Well, I mean, it really just depends on why you got something wrong. You know, if you get something wrong because you did I forgot to fully reduce the radical or something. I mean, or I literally just did some bad math. I mean, that's not those are problems that never even concern me. The problems that concern me are, I looked at the problem, I have no idea where the numbers are supposed to go. I don't even know what I'm doing. I mean, those are the problems that scare me as a teacher type thing. All right, especially when, I make a big point about this and half the class are like, I'm not sure why he's making a big point. I got this. It wasn't that hard. There's one or two that are always in the class that are so lost, they do nothing about it. Right there. All right, here we go. There's 1 through 26 all. I really did that? Yeah. Okay. Number 1 is 2 root 3. Number 2 is 6 root 2. Number 3 is 3 root 5. Number 4 is 5 root 3. Oh, I know I gave them all because we do this. I wanted to make sure we did 1 through 15 all for sure. Number 5 is 20 root 2. I won't give you a really challenging one like that on a test. That number's way too big. Number 6 is 3 root 6. Number 7 is 18 root 10. Number 8 is 8 root 7. Number 9 is 6 root 5. Number 10 is 5 root 7. Number 11 is, okay, here come the ugly ones. Square root of 21 over 7. Yes. Those are the ones that you had to rationalize. Number 12 is 3 root 5 over 5. 13 is 6 root 3. Just quick side note on these rationalized ones. So this thing that we're doing that has very limited applications in geometry, rationalize the denominator, you're going to use this in Algebra 2, and if you take pre-calc senior year, you're going to use it in pre-calc almost all the time. Oh, I got to rationalize this because there's a square root in the denominator. If that's something you struggle in, it's worth putting the effort right now. So you get that out of the way so that when you see it again in Algebra 2 pre-calculus, you're like, okay, it's no big deal. Or you go to college, take calculus. You have to be able to rationalize the denominator. Number 14 is 4 root 2. And number 15 is the square root of 3 over 9. 15 is pretty ugly. All right, so what the class was really on was the 16 through 26. All right, so 16, once again, it always hurts my soul as a math teacher when I will put a question like 16 through 21 on the test, and I have kids that will put a question mark. Like, I don't know what to do there. Take the two numbers, multiply them, and take the square root. That's it. That's the geometric mean. So the geometric mean for number 16 is 6. Number 17 is 9. Number 18 is 35. Number 19 is 10 root 10. Number 20 is 8 root 6. And number 21 is 11 root 10. And then for the meat, the true purpose of yesterday's class was corollary 1 and 2 for the rest of them. All right, 22, the answer is 2. 23, the answer is 9. 24, the answer is 3 root 2. 25, the answer is 3 root 5. And 26, the answer is 6. All right, and I'll just make the speech one more time. If you really screwed this up, I mean, don't let this sit there and fester. See me for tutoring. I can absolutely help you out on this stuff. All right, Seth, you want to grab the homework?
Yes, sir.
You.
Only 1 year.
You have to explain that. Oh, pit bulls. Okay, makes sense. All right. I should have understood that. But...
I didn't miss anyone, did I? I didn't think I did.
Do you have how many do you have? Well, how many is too many? 8?
No.
Okay. 4. 5? Jenna, if you're on, congratulations.
That's been
Oh, thank you.
All right, there's your homework. Copy down. Hey, it's Today's an easy day. Easy day. Easy day.
Oh, I love easy.
Yesterday was, well, I mean, hopefully it turned into an easy. I mean, still, doing the homework was a bit of a chore, but if you understood what was going on yesterday, you might say, well, that wasn't that bad. Today is easier than that.
Nice. Think I can get it done in class?
It depends on how much you remember from last year, solving quadratics.
Oh.
There's only a couple of them. We're going to probably spend too much time on the solving quadratic portion than we need to, but it's good effort because the solving quadratic thing doesn't go away. Like next year, algebra 2 and then into pre-calc, you're going to use it all the time as well. So, I mean, I'm going to have a couple, probably more than what the book has. I think I only assigned, how many of them are quadratics tonight? There's only a few of them that are quadratic tonight that you have to do. Number 1 through 18 all. Which ones are quadratic? Number 12 is quadratic. Number 9 is quadratic. But yeah, we'll spend some time on the quadratic ones. All right, we good? All right, here we go. Hey, Pythagorean theorem. I already know how to do this, right? You did this in pre-algebra. You did this in algebra 1. We're going to do it in geometry. At no time in pre-algebra when you first learned this, 8th grade, or last year in algebra 1, was it ever proven to you? Like the teacher just said, hey, a squared plus b squared equals c squared. Trust me, it's true. If you had me as your teacher, I showed you a video of a guy pouring liquid into 3 squares that surrounded a triangle. That wasn't a proof. That was a video, right? We're going to prove it today. And you're going to see why I didn't prove it back then, because you didn't have the mathematical knowledge to prove it. All right, so last class we dealt with this basic shape, remember. The shape starts off with a right triangle with an altitude to the hypotenuse that creates these 3 right triangles. We proved that they're all similar, and we get that corollary 1 and corollary 2 thing. Corollary 1 says that the altitude, right, that part right there, is equal to the square root of this piece, I'm pouring the AN, times this piece, NB, or BN. Corollary 2 says that the short leg of the large right triangle, in other words, AC here, is equal to the whole piece, AB, or the square root of the whole piece, times the shorter piece, the AN. Chris yesterday was saying 2/3, 1/3. Okay, if that works in your brain, yeah, that's what it kind of looks like, right? And then the last one, corollary 2, talks about the long leg of the big triangle, and that's equal to the square root of, once again, the whole thing times the piece. For me, I don't think about it as 1/3, 2/3. I think about it as the piece on the right and the piece on the left, and that works for me, but might not work for you. If this is in your notes, you'll be fine. It's just a drill of plugging in numbers and chugging through a calculation. Now, these were 3 different things about a right triangle, but when most people think about a right triangle, they don't think about this thing. They think about, I say, hey, we got a right triangle. You immediately think Pythagorean theorem, right? Okay, so let's talk about Pythagorean theorem. My favorite proof in geometry, this one right here. So here we go. We have to prove the Pythagorean theorem that a squared plus b squared equals c squared. A seemingly impossible thing, but from what we had yesterday, it ends up being a very easy proof. And it's also why I didn't prove it to you in pre-algebra, because we didn't have the thing from yesterday in pre-algebra. Secondly, just some background stuff on the Pythagorean theorem. It is a badge of honor for a mathematician to come up with a unique proof of the Pythagorean theorem. I will show you one of, I don't know how many there are, but there's lots of them. In fact, we have a president of the United States who came up with a proof for the Pythagorean theorem all by himself, right? I don't forget if it was Garfield or, I don't know, I can Google it.
Nixon.
It wasn't Nixon. But one of our presidents came up with a unique proof of the Pythagorean theorem. Okay, so here's how I choose to prove it, because I like this one. This is also the one that's in the book, too. What did we learn yesterday? What did we learn yesterday? Our right triangle had an altitude. So what I'm going to do is I'm going to make that altitude. I got to get to that thing right there. So the first thing I'm going to do is I'm going to make this look like what it looked like yesterday. So Karis said make that thing right there. Okay, so we'll make that thing right there. I'm going to call it, well, actually, I'm calling it nothing, but that does break the bottom part into two pieces that I will now call D and E. Okay. Now I need to get to a squared. Well, where is A? A is right. Oh, wait, it kind of looks like yesterday. So yesterday we could say something like, Cadence, we could say that A is equal to, remember? Well, we got to have the square root of
C.
So the whole thing, which is C times
D.
No, it's E.
E.
Okay. Further, I could say that B is equal to the square root of, you want to do that one? It's the same pattern, just opposite.
C times D.
Perfect. Okay. All right. Great. But where are we going? What's it got to say? It's got to say A squared. It's got to say B squared. This says A and this says B. So how do we make A say, and this is a stupid question, but how do we make A say A squared? We square both sides. So if I squared both sides, this would now say A squared, and what would it do to the square root symbol? It would get rid of it. If I want to say that, say B squared, square both sides, what would that do? Okay, and that's where I get this statement right there. Sorry, you learners, I wrote that on the board, you couldn't see that. But all I did was to get to this line right here, we'll simply take the information that we had yesterday, those two corollaries, write them out, and then square both sides. So check it out. Now I got an A squared, and I got a B squared. What does it say we need to do with the A squared and the B squared? I need to add them. So, oh, by the way, that's just corollary 2 of Theorem 8.1. So all I'm going to do is take these two statements right here and add them. Literally, take the two and add them. So I would get A squared plus B squared equals, well, ugly, C times E plus C times D. Okay? I mean, all that's just adding. What do you notice about this and this that they have in common? So let's factor out a C. All I did was factor out a C. What's this say right here? Well, that's factoring. What's this say right here? It says E plus D. Now look at the picture. You see that what Cadence just said? Hey, that's just C. What's C times C?
C squared.
And you're done. You just proved the Pythagorean theorem. Now, why do they show this in pre-algebra? Because this relied on the fact that we used Theorem 8.1, which no kid in 8th grade knows about. Okay. All right. So we just proved the Pythagorean theorem. Now we can use it. Okay. Cool. So somewhere in your book of truth, right? Let's do the Pythagorean theorem. Now, the only thing I don't like about our book is they draw the triangle to my eye. Looks to me like it's upside down, right? Most books, when they do the Pythagorean theorem, right, they put the triangle like this. I mean, it doesn't truly make a difference, but to my eye, I like my right triangle to look like this, right? So in your book of truth, Danny, make sure that you have the Pythagorean theorem. The Pythagorean theorem says, first off, you got to have a right triangle, but the sum of the square of the two legs is equal to the square of the hypotenuse. The sum of the square of the two legs, A and B, is equal to the square of the hypotenuse. In pre-algebra, algebra 1, they give the definition a bit more detailed. They'll say something to the effect of, if you have a right triangle with legs A and B and hypotenuse C, then the square of the sum of the two legs is equal to the square of the hypotenuse. In geometry, we just kind of cut that part out. But yes, A and B have to be the legs, C has to be the hypotenuse. Does anybody know where this line comes from, or where it's used? You ever seen The Wizard of Oz? It's one of the last scenes in The Wizard of Oz.
Back where I come from, we have universities, seats of great learning, where men go to become great thinkers. And when they come out, they think deep thoughts, and with no more brains than you have. But they have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum P Pluribus Unum, I hereby confer upon you the honorary degree of PhD. PhD? It's Doctor of Thinkology. Some of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, John, I've got a break. How can I ever thank you enough? Well, you can.
And it actually turns out he screws up the Pythagorean theorem. Because he says of an isosceles triangle. We need a right triangle, not an isosceles triangle. So it's always been a debate among mathematicians when, I forget the guy's name that wrote the book, that when he did that, did he truly make a math mistake, or did he make the scarecrow make the math mistake as an ironic pun of the fact that he really isn't that smart? You know, we don't know. But okay. How many people have never done Pythagorean theorem before? No one, right? Everyone's done it before.
No.
So recall, we're dealing with right triangles. The hypotenuse is the side that is opposite the right angle, and the other two sides are called the legs. So this would be a pre-algebra problem right here. Like, I mean, I don't know if I stole this from pre-algebra. It's an example from the book, but this is pre-algebra. Danny, set it up. This is box 2.
So put A and we can put C equals A and B.
We got a square though, right?
Yeah.
So,
Put 2 on
so what do you want me to write?
there. That's 2
X squared would be equal to?
3 squared plus 7 squared.
Perfect, good job. Okay. How can you screw this up? You just don't identify what's the hypotenuse. It really doesn't matter which one is A or B, but you definitely have to make sure that C is the hypotenuse. So we plug those numbers in. I don't want to insult your intelligence. We just do the math. All right. 3 squared is 9, 7 squared is 49. We add those together. Looks like we're done, except we're not done. What do we have to do?
You have to.
I'm going to take the square root. Okay. So the question is, are there any perfect squares in 58? Okay, well, then you're going to spend some time once again thinking about, are there any perfect squares in 58? And they're not. Okay. All right, cool. There's a pre-algebra Pythagorean theorem. Here's a geometry Pythagorean theorem. All right, so go ahead, set it up.
Wouldn't just the missing side be 3 because we just calculated that?
Well, this
A
is,
squared plus B squared.
thank you for noticing that, but I was hoping you didn't notice that.
Oh,
Let's just say these are not the droids you're looking for. You didn't know that, but very good.
oh.
You're the only student in, I don't know, 10 years to notice that.
So what else am I gonna do?
Well, let's just say you just walked into the classroom and you saw this problem. And I said, hey, do the Pythagorean theorem. What would be the setup?
I don't know. I guess I would
It
have.
says calculate the unknown side. So what side is unknown? This one right here.
I would try to divide 58 by 7.
How about we just use the Pythagorean theorem?
That's a good thing too.
Okay, so give me the setup, just what Danny just did. Give me the setup using the Pythagorean theorem.
A would be 7 and B would be 58 squared.
Okay, we're going to go back to the picture. Where are the sides, the legs, compared to the hypotenuse? The hypotenuse is the side that's opposite the right triangle, right angle. And we know that for Pythagorean theorem, that C, that is the side that is opposite the right angle, is the letter that's all by itself that's squared.
Yeah.
So that's what you got to keep in your back of your mind when you do this problem. Okay. So now just give me the setup, and you can call that any letter you want, actually.
So this would be B squared plus C squared equals A squared.
Pythagorean theorem is always A squared plus B squared equals C squared. Never changes.
So I guess A wouldn't really.
And it doesn't matter which one you call A. You want to say that's A or you want to say that's A, it doesn't matter.
Okay, so it's just like a squared plus 7 squared
Equals
50 squared. No, it's
square root of
square root of 50.
squared.
Yes.
Because remember, it's always A squared plus B squared equals C squared, and then you're just plugging in numbers, okay? So that is your start, and you plug in your numbers. Now, I agreed that I call that A squared as well, too. All right, but one more question. What is the effect of squaring on a square root symbol?
It just takes away the
Just takes it
square.
away. Do a little bit of algebra. Subtract 49 for both sides. Last step.
Square 9.
Take not square 9, but you're just using the wrong word. Not square 9. How do we get rid of squaring?
You do that thing. Wait.
That thing is called the.
Yes, square root.
Right. Were you thinking of that and you just couldn't get the word out?
Yeah, I was thinking of square root.
And that's what I thought as well, too. And by the way, you told me from the start that this is
3.
right. You told me that at the very start. So, point being is that even when you're going to get these weird, and you will tonight, I mean, they're going to be weird things. Don't panic. Just do the Pythagorean theorem. All right. Quick side note. This is we're going to take a solid 5 minutes and talk about this. Danny, you paying attention? Okay. In Algebra 1, you learn this skill, right? Because we're going to get variables involved, and the Pythagorean theorem involves squaring. When you square a variable, you get a quadratic. You get an x squared. So we get something that potentially is going to require us to factor. Okay? So let's just review factoring quadratics. Here are 2 quadratics. This is box 3. Okay? All right. In order to factor a quadratic, it's quadratic because x is squared. In order to factor a quadratic, you need to have it set equal to 0. That's always step number 1. Okay, so these are 2 different examples here. So the one on the right, we're good to go. It says equal 0, yes?
Yeah.
Does this say equal 0? So guess what the first step is going to be? Make it equal 0. So how do you make this equal 0? We're going to add 4 to both sides. Yes? If I add 4, that 8 turns into a 12. There's my first step. Okay, now they both say equal 0. I can factor them. All right, who remembers how to factor? How do you factor quadratics? Hence I said we're going to spend 5 or 10 minutes on this. Rarely do I get algebra or geometry students that immediately remember this. Okay, way back when, it was almost a year ago that you learned it. You remember it now?
Do you like find numbers that add or multiply?
To what numbers? Okay. She's very close. She said, I'm looking about something to add or multiply that's 12. Does it stimulate your memory a little bit more? All right, you guys need to write this down then. All right, here's how you factor quadratics. We are looking for, because we're trying to factor, we're looking for 2 numbers that multiply together that equal, help me out, but add to 7. I'm looking for 2 numbers that multiply to, not 15, that add to -2. Okay? You remember now? Okay. So for me, whenever I tackle one of these factor problems, I'm going to be stupid and start with 1. What times 1 is 12? Does 1 times 12 add up to 7?
No.
1 adds up to 13. So it's not 1. 2. What times 2 is 12? Does 2 plus 6 equal 7?
No.
What's the next number? What times 3 is 12?
4.
Does 3 times 4 add up to 7?
Yes.
All right, you just found the answers. So we know that for that first one there on the left, that it's a +3 and a +4. Why am I writing +3 and +4? Because remember, eventually we could get negatives involved, right? There's 2 more numbers, -4 times -3, that multiply to +12, but -4 and -3 don't add up to +7. Okay? So we know that. Do you remember what you do next with these 2 numbers? Okay, the next thing you do is you write it like this. You take x and you write plus 4. You take x and you write plus 3, and you surround it by parentheses. Oh, by the way, when you multiply these two together, you get back to this. X times x is x squared. 4 times 3 is 12. 4 times x is 4x. X times 3 is 3x. 4x and 3x is 7x. So backing up, what two numbers multiply 12 to add up to 7, 4, and 3. By the way, you could write that as 3 and 4. It doesn't make a difference. Then we take these two numbers along with the variable x, and we do this parentheses drill. Stop me if you're lost. I mean, you did do this last year. Okay? Do you remember what you do next? We take each one separately, x plus 4 and x plus 3, and we set them equal to 0. Why do we do that? What does this say the answer is?
0.
How do you get 0 if you're multiplying? If this is 0, or this is 0, or they're both 0, right? That's the only way through multiplication do you get to 0. Either the first thing is x plus 4. If that equals 0, well, then 0 times, I don't care what that is. 0 times this would be 0. Or this is 0. X plus 3 is 0. Or maybe they're both 0. So that's what we do. We take both of these separately. We set them equal to 0 and solve. Oh, by the way, it's pretty simple to do. If that equals 0, what does x equal?
Negative.
If this equals 0, what's x equal to?
-3.
And those are actually the two answers, -4 and -3. How do you factor or solve a quadratic? Well, you do it by, or how do you solve a quadratic through factoring? This is the process. You see why I said we're going to take 10 minutes to do this? Because none of you remembered it. So let's do some. All right, take a look at the second one on box 3. Here we go. Bailey, I said I'm stupid, so I always start with the number 1. 1 times what is -15? 1 times what is -15? -15. Does that add up to -2? Nope, it's not that. 2 doesn't go into 15. Is 3 going to 15? 3 times what is -15? What? -5. Do these two add up to -2?
Yes.
And you're done, right? We're going to follow this pattern. So it's 3 and -5, or +3, and it doesn't matter the order that you write them. Okay? There's no special, why do you write -5, 3, not 3, -5? I don't know, because I typed it that way. I'm going to do the same thing. You see what I did? Once I get this, I'm going to write x minus 5, x plus 3 equals 0. Okay? What was the next thing I did?
You divided like
I took that piece,
yes.
and I took that piece, and I
Equal to 0.
set them equal to 0. By the way, no one actually does this. You know why? Because after a while, you see the pattern. Solve that. What do you get?
+5.
Solve that. What do you get?
-3.
So what's the statement I'm about to make? Just change the signs, right? There you go. Solved. Danny, how many of these did you do? Okay. All right. Now, because it's geometry, right, they assume that, well, you're experts at this, right? And they immediately jump to a harder one. So this is a slightly harder one, right? This is a standard one that's slightly harder. Okay. There's actually an extra step that I didn't talk about. The first step is always set it equal to 0. Does it say equal 0?
No.
So what's my first step?
Subtract 20.
Subtract 20 from both sides. You with me? I apologize. I chose to do it differently. Let's do it the way I just said. If we subtract 20 from both sides, we'd get 2x squared plus 22x. Subtract 20, we get what? Plus 36 equals 0, yes? If you can, it only happens occasionally, notice we can factor a number out of all of these. What goes into all of these evenly? 2. So all I'm going to do now is divide everything by 2. If I divide this by 2, this by 2, and this by 2, and I do have to do it to the 0, what will we get?
11, like, so you get x 11.
X squared
Yes, x squared 11x
plus 11x
plus 12.
plus 18.
Yes.
Okay. So that's what you do. Now you're going to see me now that I erased this and write what I wrote. I went ahead and divided everything by 2 from the very start, and then I did that process, but we still get the same answer. Okay. So it doesn't matter if you do your division first or you did it what I just showed you there second, it still gets you the same answer. Cool. Now we need to look at what 2 numbers. Okay. 1 times
1.
you get 11. I said 1 times 18, we get 11. Bailey said no way. 2 times
Oh, I forgot we were doing this.
we get 11. We're there. It's 2 and 9. 2 times 9 is 18. 2 plus 9 is 11. All right.
Negative 9 and negative 2.
And now he sees the pattern. Like I said, very rarely will I get anyone to actually write that step that I showed you on the previous one. Most people immediately go, oh, it's -2, -9. The book will always write them in increasing order. So they'll put -9 first, -2 second. Yep. Cool? All right, see if you can do this one all by yourself. Box 4, the second one, without me walking through any steps. Okay, you know what to do? Okay. Connor? Okay, Connor. Give everyone about a 20-second head start, and we'll do it together. Bailey, Parrish, you guys good? All right, Connor, we're going to look at 2 numbers. This number is, and this number is, sure you do. Turn your head behind, look behind you. Yes? Okay, so I'm looking for multiplication. I always start with 1. I just don't want to see it. What 1 times what is -20? Does that give me +1 if I add them together? No. What's the next number? Don't overthink it. What comes after 1? 2 times what is -20? -10. Do these 2 add up to 1? What's the next number? 3 times, well, 3 doesn't go to 20. What's the next number? 4 times what is -20? Do these 2 add up to +1? That's up to -1, so it's close, but what's that? Miss Chartier's room. Yeah. Do you know the number? Okay, I have the combos, but I don't have the numbers. Okay. Sure, I can do that. All right, bye. Sorry, guys. Phones are so 20th century. All right. You see what I did there? I mean, originally we said -5 and that guy was -1. Well, when you do that, you just swap the signs. Okay, so those are my 2 numbers. And I'm going to write this. So tell me what to write.
X minus 4.
Quantities.
How do you know the 4 is not -5?
Because remember, we're trying to get to +1. I mean, I initially guessed it was -5. And as soon as when I added and I got a -1, I'm like, oh, just flip the sign and I'll get the opposite. Okay. All right. Yes? Okay. Therefore, the answer is
4 -5.
okay, 4 and -5. Cool. All right, there's our 10-minute segue into solving quadratics. Right? Yes? Okay. But you're a big kid now. Now you can solve quadratics. All right, so here we go. This is what will look like. There's only 1 or 2 of these tonight for homework. By the way, it's just the Pythagorean theorem. So, Karis, just give me the setup. Just now, don't overthink this. It's just the Pythagorean theorem. So she said x squared plus the quantity x plus 2 squared. There you go. You did it. Okay. That's all we're doing. Now I chose to write a different order. There's no special reason why I did that. Okay. Well, x squared is great. We got to square x plus 2. All right. We got to square that. So we got to do x plus 2 times x plus 2. Are you guys, I always like to stack them. That's me. Do you guys do the distributive property or do you like to stack them? Bailey? Distributive. Okay. 2 times x. 2 times 2. And it's positive, right? And then we got to do this one. X times x. And x times 2. Another positive 2x. Now we group what we can group, 2x and 2x's.
4x.
So I'm going to erase all that and write that. See what it is? There's your x squared plus 4x plus 4. Yeah, because 10 squared is 100.
Oh.
Okay. Cool? All right. Hey, I grouped that one and that one. That would give me
8.
no.
No, wait, which one?
X squared. I'm sorry. There we go. X squared and x squared would give me.
2x squared.
And if I move the 100 to the other side, 100. I'm sorry. 4 minus 100 is negative 96. See what I did? I did 2 steps in one. They all have what in common?
Letter 2.
A 2, right? I can divide everything by a 2. If I divide everything by a 2, that turns into x squared. That turns into 2x, and half of 96 is a number, right? There you go. There's your number. All right. 48 and 2. 1 times, not 2. 2 times,
3.
2 times 24, still not 2. 3 times 16, 3 and 16, you don't get 2s. 4 times, still not 2. Boy, we're running out of numbers here. 5 doesn't go in there. 6 times,
8.
oh, 6 times 8,
48.
we get a 2. Right? 8 minus 6, right? We got an 8 and a negative 6. You see how I did that? When I typically have students that can't do this, they'll look at this number and they'll immediately start with, I don't know, numbers. And then they'll say, well, that didn't work. And they'll try to think of another number. I always start with 1, even when it was ridiculous. 1 times 48 is never going to get me to a 2. I still start with 1, and then I go 2, and then 3, and then 4. The only time I skip it is when it doesn't go into 48. But that way I don't skip over a number. Oh, by the way, what's the answer here?
Negative 8 and 6.
There's a problem with that. What am I claiming?
X equals,
Say it again louder.
X equals negative 8 and 6.
A side can't be negative.
Uh-oh.
So you've now reached a really big moment in your math career. Occasionally in math, you get to a true answer that has what we call is an extraneous solution. Yeah, these are the 2 answers to this quadratic. But only one of them makes sense with our problem. Which one makes sense?
6.
So x is 6. Okay. This will happen not all the time, because remember, we can solve a quadratic and get 2 positive answers. But occasionally we get a negative and a positive. Occasionally you get 2 negatives. Right? It ain't gonna happen in this one because there's no way one of those sides can be negative. Okay. That's pretty big boy, big girl stuff right there. I mean, that's a lot of work, and it's just the Pythagorean theorem. All right. I do want to do, let's see, one more, just because we should do one more. So this is, I forget what page, but it's on the classroom exercise. Go ahead, Karis, pick one. Let's do 14. All right, set it up, Bailey. Set it up, 14.
4 squared plus 6 squared.
Okay. 4 squared is
Oh,
6 squared is, and x squared is still x squared. 16 and 36 is 50. And then the last step would be to any perfect squares in 52? I think there is. We start off our perfect squares. The first one we start off with one doesn't help.
0.
So we're always going to start off with 4. Does 4 go into 52? And remember, on the test in front of your hands, you're going to have a. So you're going to take, how are you going to figure out that 4 goes into 52? You're going to use your calculator if you need to. You're going to do 52 divided by 4 and think, oh, wait, it goes. Somebody help me.
Oh.
What perfect
13
squares?
times.
13 times. So 52 can be written as 4 times 13. Therefore, the final answer is
2 square root of 13.
2 root 13 equals x. That's a lot of work. It's not pre-algebra Pythagorean theorem, it's geometry. All right, Connor, pick one.
17.
Which one?
17.
17. He's picking an ugly one. All right. Chris, set it up. Set me up with the Pythagorean theorem, number 17.
X squared times
Plus
plus x squared,
equals.
whatever that is squared.
Yeah, and some of you can take a shortcut step, right? What do you do when you square? What happens to the square root symbol? Goes away, but you still got to square 7. That's 49. So it'll be 49 times 2, which is 98. See what I did there? Okay.
So it's
X squared and x squared is.
2x squared equals 98.
Now what?
Divide by 2.
Divide by 2. Half of 98 is 40,
Something.
40, 40. Therefore, x is. That wasn't bad at all. Notice I skipped writing square root because I'm lazy. But I did take the square root. Did everybody follow what I just did there?
Yeah.
Cool. Danny, pick one. 18 is a little bit more challenging than 17. Okay, set up, Danny.
X squared is equal to
Plus,
plus 2 squared.
it's a squared plus b squared. A and b are legs, not the hypotenuse. So good. X squared plus, which one is the other leg?
5.
Yeah. Can you square that in your head? You don't have to. Can you square that in your head? 25 times
Takes away the 3.
times 3. 325, so 3/4 is 75. So plus 75, keep going, Danny, equals.
7.
You said this squared plus this squared equals a squared plus b squared equals c squared. 2x quantity squared. If someone gets in a problem, look up here. This is the one that'll kick your butt. Because what you really think and you want to write is 2x squared, and it's wrong. It's parentheses, the whole thing squared. So I got to square the 2 and I have to square the x. So it's not 2x squared, is actually perfect. Move the x squared to that side.
3x squared equals 75.
Now what?
Divide by 3.
Ooh, this one ends up being very nice and friendly, even though it looked ugly at the very start. See what I did there? Therefore, x is equal to,
5.
and you're done.
Must be the money.
15 is actually the hardest one up here.
15?
Yeah. All right, we'll do that one, call it a day.
Yeah, because you have to find something that's 25.
All right, set it up.
What? No,
Now, why is 15 hard? Well, look at the shape. What did they do with the triangle?
Flipped it upside
It's upside down.
Killed it.
yeah.
So you really, if you make a mistake, you're going to say that's A and that's B and that's C, and it's not. That's, well, it doesn't matter which is A or
That's
B.
leg.
That's a leg and that's a leg.
So it's gonna be 25.
He
plus
did
X
5 squared plus X squared, and that equals,
Go around squaring
X squared
things.
plus 1.
so I gotta square that. In other words, I gotta do X plus 1 times X plus 1. She said she likes doing the distributive property, 1 times X, 1 times 1, X times X, and X times 1, another X. So we had X squared plus 2X plus 1. X squared plus 2X, and I'm running out of space. Ooh, look at that. Right? Sometimes you get lucky. The X squareds are on opposite sides, so when you subtract that from both sides, they go away, and you're left with 25 is equal to 2X plus 1.
Just take away the 1 and then just 24.
Subtract 1. Therefore, X is equal to,
Oh, I thought it was 2. Thank you.
and you're done. That was pretty cool. Okay. Questions on anything we did? Pythagorean theorem is easy in understanding what to do, but clearly, occasionally, we get these really ugly answers. So tonight for homework, I gave you 1 through 18 all. Which ones are the ugly ones? They're not all that ugly.
12 is actually kind of.
12 is,
I still don't know how to say that.
okay, so where is the right angle on number 12?
It is split.
Look at
It is
his.
by the angle.
And it's
by-
like, how do I know it's, but we'll look at, I see a 45, 45, that's a 90.
Oh.
If one angle of a quadrilateral is 90 and
the-
all the sides are the same, that's the other thing it's gotta be,
Yeah, all the same.
then it's a square. So the right angle is top and bottom, left and right. So if we set that one up, it would be X squared plus, keep talking,
So it's gonna be plus
X squared plus, and that's gonna equal,
just 6 root of 2.
so that'd be
times
36 times
square. Yeah,
2.
36 times 2 is going to be
72. So that gives us 2X squared. This is this problem
Yeah.
right here.
You divide both sides by 2, then you get 36, and then square both sides and you get 6. That's 6.
So sometimes it looks like it's going to be complicated. It's actually not too bad. 12 is not the ugly one.
I would say,
Or if you're body shaming now.
I would say maybe 9,
Maybe 9.
8.
I mean, 12 is hard because you had to think about it, but the actual application of the Pythagorean theorem wasn't too bad once you did it. All right. Finished with 1 minute to go. Gianna, do you have any questions?
No, I'm okay.
Cool. Well, we're going to stop it right there, Gianna, and we will see you tomorrow.
Okay, bye-bye.
See ya.
Bye, Jenna.
Bye bye.
Bye, kids.